There we go. Now that that's recording, I love it. Confidence. I will be ready. Well, hopefully we'll all be ready. First exam is Monday. So what I want to do is my level best to finish up, chapter 1 today. So Friday, we can address questions you have with any homework assignment, homework problems, work through some examples, do whatever we have to do to get y'all familiar with and comfortable actually working through the mechanics of these exercises, of these problems. Okay? Because we really do want all of you to do exceptionally well on the tests. Now, and yes, come prepared. Actually, come to every class. I'm always happy to start the class by addressing one or two questions about any of the homework problems that have given you difficulty. I can try my level best to make all of this clear to you, to explain all of this material in a way that makes sense, that you can understand, but not without feedback from you. I need to know what it is that's giving you problems before I can help try to clear it up. I hope that that's what we'll accomplish by working through some of these homework problems and any of them that give you difficulty, to clear up any misunderstandings, or maybe to, at any rate, and yes, it's, you do get some points for your homework assignment, but I would rather help you work through them in class and let you get the points. If that means that it'll help you better understand the material and be better able and prepared to pass the exams, because the exams is where the bulk of your points are coming from. So, on that note, let's start off with, do any of you have any questions about any of the homework problems yet? Anybody have any of this is giving you difficulty? Anything that's been confusing yet? Okay, well, give me time, we'll get there. I will confuse you before the end of this. No. Nope, just need a pen and a calculator, and like I said, you can have a 3x5 card with anything on it you want, front and back. Just don't try to get copies of the questions first. If I see you've got any of the questions on your 3x5 card, then you and I are going to Vegas, because the questions haven't been written yet. Let's pick up here in chapter 1. We'll go back and review a little bit. We talked about units and the difference between fundamental, or what the book calls base units, and derived units. And the example I used was the Newton, which is a kilogram meter per second squared. It's mass times acceleration, or a unit of force. We also pointed out, we looked at the different kinds of units, and by that I don't mean different fundamental units. I mean different systems of measurement. We looked at the Système International, SI units, MKS or CGS. Who remembers what those stand for? Meters, kilometers, and seconds. What does CGS stand for? Centimeters and grams and seconds. Physicists, engineers typically use MKS. Biologists, chemists typically use CGS. Okay? And I think I even pointed out an example of where NASA blew up a bajillion-dollar spacecraft when they shot Mars, because one group was working in English units and nobody else noticed and nobody did the conversions. We talked about converting units. If you needed to convert meters into miles, where would you start? Think about significant digits. Remember, we always come back to significant digits anytime you measure something. Well, the definition of 1 inch is 2.54 centimeters. Now, what does that mean when you start thinking about significant digits? Or let me ask this another way, and this is a trick question, so think before you blurt the answer out. How many significant digits are right here? Any more guesses? No. That symbol means this is a definition. So 1 inch is no longer an inch is no longer 1/12 of the length of the king's foot. 1 inch is defined as 2.54 centimeters. That is a definition. That means it is exact. It has as many significant digits as you need. If you're working with measurements where you've got 5 significant digits, then you write that as 2.5400. Okay? What if you're working with measurements where you only have 1 significant digit? You can still write 2.54 just to keep the calculations as accurate as possible. But at that point, you could just as easily write 3. Because 2.54 rounds to 3 as 1 significant digit. Everybody tuck that away in the back of your head because it's coming up here in just a little while in this lecture. On page 10, I want to direct your attention to this. They give a table 1-5 that lists some of the base or fundamental units. And they are meter, second, and kilogram for length, time, and mass. I told y'all that they have decided that the ampere is a fundamental unit of electric current. Remember, I don't think, did we talk about Lord Kelvin on the first day of class? How he was the one who said that once you can describe something mathematically, then you can truly understand it? And that's a paraphrase. Well, here's his namesake. The Kelvin is the fundamental unit of temperature, where 0 degrees Kelvin is absolute zero. In chemistry, there's a fundamental unit called a mole, which is Avogadro's number. You know what? It's 6.022 times some big exponent, 10 to a big exponent, and I don't remember exactly what it is, but it's the number of atoms in 1 mole. A mole of any substance is Avogadro's number of those atoms. And no, I don't think you'll be needing that in this class. And then, of course, candela is luminous intensity, or how bright a light is. These are fundamental units. And quite frankly, in reality, in all of them, in every case, they're kind of arbitrary. They're made up. Someone once accused me of, when I was giving a speech, someone accused me of using a made-up word. And I think it was paraliterate, is a word I made up to describe I'm from South Louisiana, the indigenous people. In fact, my name, Hebert, is from the Acadian French language, Cajun French people. Until 1976, there was no written form of the French language. In 1976, some Catholic priest in Lafayette published a dictionary and a lexicon for the Cajun French language. Until then, there was no written form, so anyone who spoke Cajun French was, by definition, illiterate. They didn't have a way to write their language. And so I called it paralliterate. Someone accused me of using a made-up word. I said, well, duh, they all are. It's true. The same thing is true of units. They're made up and they're defined. And once the definition is accepted, then that's the way it is. The book talks about some of the standards that they use, the platinum rod. Has anyone read the book? Just out of curiosity, who knows what the original intent was for the measure of 1 meter? It was 1/10,000,000th of the distance from the equator to the North Pole. That was what they originally thought of as, we'll call that a meter. Okay, how long is that? Oh, well, and then the arguing began. Anyway. We've looked at converting units. And when you do convert units, you want to start with a definition. 2.54 centimeters is defined as 1 inch. So if you're converting from English to metric, this needs to be in there. Now we also know that 1 foot is defined as 12 inches. 1 yard is defined as 3 feet. 1 mile is defined. Who knows the original meaning of a mile? What was 1 mile? No. The definition today is that it is 5,280 feet. Originally, a mile was the distance that a Roman legion could march in a certain number of steps. You see the point? You don't need to know that for any of the course material, but the point I'm trying to get across to you is how arbitrary some of these things are. We know that a foot was originally the length of the king's foot. That's why it's called a foot, because his foot was 12 inches long. You know, if you've ever been to Sunday school, you know Noah worked in something called cubits, which is the length from your elbow to your fingertip. Well, I've never met Noah, so I don't know how many inches were in one of his cubits, but I'd bet money that every one of us in this room would have a slightly different cubit. That's the reason why we've worked at standardizing and defining these units in reproducible ways, because that ties back to repeatability, precision, and accuracy. Everybody remember those 2 words. And in case you haven't noticed, I'm sneaking in some review for the coming test. Can anyone tell me the difference between precision and accuracy? Precision is about repeatability. How many significant digits can you repeatably measure consistently from one measurement to the next? Accuracy is how close those measurements are to the actual length. Okay? You could have the most precise ruler in the world, and you might measure the length of this room as 10 feet 2.75 inches every time. That's a very precise ruler. It's also a very inaccurate ruler because this room is obviously a lot more than 10 feet long. That's the difference between precision and accuracy. Okay, converting units, you treat them algebraically. If we want, in fact, let's work through an example here. They talk about an example of how tall is an 8,000 meter peak. Okay, they list however many 14 mountains in the world that are over 8,000 feet tall, and they ask, how many feet is an 8,000 foot mountain? So let's work through this. Well, we know that 1 foot is 12 inches, and we know that 1 inch is 2.54 centimeters exactly. So we can immediately convert feet into meters by writing 1 foot, if our marker works, 1 foot per 12 inches. We know 2.54 centimeters per inch. What else do we know? We know 100 centimeters per meter. What else are we going to need? We've got 1 foot per 12 inches, 2.5 centimeters per inch, 100 centimeters per meter. Are we going to need anything else? Let's find out. We want to start with 8,000 meters. We want to convert that into centimeters. So we multiply 100 times 100 centimeters per meter. Now remember, we treat the units algebraically. So when we have a meter divided by a meter, they cancel out. 8,000 meters is equal to 800,000 centimeters. And of course, I'm doing this one step at a time. You could write out the whole conversion chain in one long multiplication, but I want to do it one step at a time. Once you get familiar with it, once you're comfortable doing it, then you can string them together as long as you need. Now, we know that there are 2.54 centimeters in every inch, so we can convert this 800,000 centimeters into inches. How would we do that? We would divide. I want to make this, I don't know if this has occurred to any of you or not, but I want to take a side moment here and point something out to you. All of mathematics reduces to addition. Okay? You start by learning that if you have 3 blocks and you add 2 more blocks to it, you have 5 blocks. So that's addition. What is subtraction? Subtraction is just addition of a negative number. Now, what is multiplication? If you think back to when you were in grade school, first grade, learning how to multiply, it's just multiple additions. 3 times 5 is adding 5 to 5 3 times. Now, what is division? Division is simply multiplication by a reciprocal. If you multiply anything by the reciprocal of a number, then you have divided that thing by that number. So division is actually just multiplication, which is actually just addition. All mathematics reduces to addition. That's why computers work, because that's all a computer can do is add ones and zeros. And it can just add them about a bajillion times a second. So we could divide this by 2.54 centimeters per inch, or we could rewrite this as 1 inch per 2.54 centimeters. And then do the multiplication. And we keep it neat so the centimeters cancel. And I can't do that math, that arithmetic in my head. So we will divide 800,000 by 2.54, and that will give us 314,960.6, so we'll call it 961 inches in 8,000 meters. And we know that there are 12 inches in 1 foot, so we multiply this by 1 foot per 12 inches. The inches cancel, and dividing by 12, we end up with 26,248 feet. Now, does everyone see how we manipulate the units and the conversion factors so that the units end up canceling to what we want? We start off with meters, we end up with feet. And that will work with all units. They work through some other examples. We could convert this into miles if we wanted to. How would we convert 26,248 feet into miles? 1 mile for 5,280 feet. They would cancel, and if we divided that by that 5280, we'd have how many miles 8,000 meters is. Real quick, how many kilometers is 8,000 meters? 8. Now that one you should do in your head. 1,000 kilometers is a kilometer. 1,000 meters is a kilometer. So, but don't risk it if it's, it doesn't hurt one bit, even for something that simple. Write it down so you can see that you're doing it right. Miles per hour. Now, I also told y'all that I need to stop reading something else while I'm thinking about what I'm about to say. Yeah, I told y'all about an error that gets snuck into the world we live in. And it's all around us, so we have to deal with it. We have to be aware of it. But we also need to understand why it's an error. And that is the relationship of 2.2 pounds being approximately equal. It's not an exact, but it's close enough for folk music and government work. How much approximately is 2.2 pounds? 1 kilogram. But only under what condition? on Earth. Thank you. Mass and weight are two different things. Weight is a force. Who remembers what the unit of mass is in the English system of units? Anybody? It's a slug. But keep that in, remember this. You're going to hear sometimes you'll hear someone talk about 1 ton versus 1 metric ton. And sometimes they'll spell that one T-O-N-N-E because they're European. 1 metric ton is defined as 1,000 kilograms, which means that a metric ton is actually a little bit heavier on Earth than a regular ton, because a metric ton is approximately equal to 2,200 pounds, as opposed to a regular ton, which is 2,000 pounds. Okay? If you live in this world, if you live in this country, whether you're working here in America or in Europe or China, you need to know when you start converting, people are going to want you to convert from pounds to kilograms, as though they're the same thing. Just know that they're not. Now, I'm going to introduce a couple of new subjects here. The first one is order of magnitude, or rapid estimation. A lot of times, if you're working on a problem, an order of magnitude estimation is all you need. You don't really need to know exactly how much something is. If you're, let's say you're an engineer working on a design for a new city or a new sewer system. Well, at some point you may have to sit down and actually start making, precise calculations of how many lengths of pipe you're going to use in order to estimate how much concrete you're going to need for this sewer system. But when people are just making first draft decisions about whether they're going to spend the money, they don't really care exactly how many joints of concrete pipe it's going to take to put in the system. What they want to know is, how much is it going to cost? Are we talking $5 million or are we talking $500 million? Now, what's the difference between $5 million and $500 million? 2 orders of magnitude. But that's all that someone's interested in. So a lot of times it is very handy, it's very convenient to be able to do rapid order of magnitude estimating. And I think the best way to explain how to do it is to work through an example. The example in the book here talks about how much water is in a particular lake. Well, just think about the problem of making that measurement. You're going to have, first thing you're going to have to do is make a precision topographical map of the bottom of the lake and the shoreline of the lake. And you're also going to have to account for, what happens if it rains? Because the shoreline of a lake can change significantly from, depending on how precise you're doing the sketch. It can change, fairly significantly if you just have 3 or 4 inches of rain. You raise that shoreline 3 or 4 inches, and all those shapes change quite a bit. but do they really? To first order, the lake is still going to be where the lake was. The lake is still going to be as deep as it was. The lake is still going to be as big around as it was. So when we're doing order of magnitude estimations, we're just completely ignoring all of those little minutia of details of how, of precision. We're basically throwing precision out the window and just getting a big round number of about how much is there. So they tell us here in the book that for a lake, this example, we're going to say that on average the lake is about 10 meters deep and on average about 1,000 meters across. So to first order of magnitude, we're going to draw this lake as a big right rectangular cylinder. 10 meters deep and 1,000 meters across, or a 500-meter radius. Now, what's the first thing you notice here? How many significant digits do I have? No, in this number. How many significant digits? 1. How many significant digits? 1. These zeros are placeholders. They just show you where the decimal point goes. They are not actual, precise measured numbers. Same here. It's 10 meters. It's closer to 10 meters than it is to 5 meters or 15 meters. Or it's closer to 10 meters than it is to 20 meters. On average. 1 significant digit here, 1 significant digit here. What if we measured this one out to 5 significant digits? What could you still say right now without knowing anything else about how we're going to work this problem? Right now, let's say we measure this radius to 5 significant digits. We find out that it is, on average, 500.03 meters. What can we immediately still say about this calculation that we're about to do? Well, that's true, but remember when you're working with significant, anytime you're doing a calculation, the final answer cannot have more significant digits than the least number of significant digits in any of the factors. Since this one still only has 1 significant digit, this is pointless because even after you do the multiplication, you can still only keep 1 significant digit. Now, based on these numbers, how would we calculate the volume of this right circular cylinder? What is the volume of a cylinder? The area of the circle is pi times r squared, and then the area times the height is the volume. So you multiply pi r squared times height to get volume. Now, how would we do that calculation here? Well, we're going to multiply the radius squared. So that's going to be 500 meters squared, which would make it square meters. We're going to multiply it times the height, which is 10 meters. What other factor are we going to throw in? Just 3. What is pi to one significant digit? 3. 3 times 500 is 1,500. Times 10 makes it 15,000. Square meters times meters is cubic meters. So we know that the volume of this lake to first order of magnitude is about 15,000 cubic meters. What if we wanted to know how many liters are in 15,000 cubic meters? I'm going to introduce you to another definition, so perk up, pay attention. 1 liter contains how many milliliters? 1,000 of them. 1,000 milliliters. How many cubic centimeters are there in one cubic meter would be 100 times 100. No, that's not right. The definition is 1 cubic centimeter, or cc. Any of you in the health? You're in health, so this one will definitely be meaningful to you. 1 cubic centimeter is defined as 1 milliliter, or 1/1000th of a liter. So if we wanted to take this 15,000 cubic meters, we could convert it. Go ahead. Oh, yes. 1 cc, 1 cubic centimeter. Is defined as 1 milliliter, 1/1000th of a liter. A liter, another way of writing this is that a liter is defined as 1,000 cubic centimeters. So using those definitions, we could convert this 15,000 cubic meters into some number of liters. Now, does everyone see how order of magnitude rapid estimation works? And this looks like a pretty interesting little practical example. Everybody look at on page 14. Look at example 1.7. I want you to they talk about estimating the thickness of a single page in this book. Now, we could go down to the lab and get a micrometer and make a bunch of measurements and then do a statistical analysis and come up with probably, I don't know what, 5/1000ths of an inch or so. But the example they use here is a way to quickly do a rapid estimation, at least to an order of magnitude, to 2 significant digits they seem to be using. They say that the book is, 250 pages, and that it's about 1.5 centimeters thick, which is approximately 6 millimeters. No, 6. That's 0.06 millimeters. Which is less than 1/10 of a millimeter. I know there's a 40 microns in a mil. It doesn't matter. The point is, it's an interesting example. But I think I'd rather work this one. How many of you know about the first time someone estimated the radius of the Earth? It was actually done back in ancient Egypt, long before even the Greek Empire came into power. And it was, I'm not going to go through the details of it here, but it was, this guy noticed that the sun perfectly lit the bottom of a deep well in one location on a particular day every year, and that it perfectly lit the bottom of a different well at a different time on that same day every year. And then he used that fact and the distance between them to come up with an estimation of the angle between them, and that gave him the radius. And we're going to do something similar, or at least hypothetically similar. We're going to use a hypothetical lake. And by the way, if any of you ever run into any flat earthers, this will be a real good little tidbit to remember whenever they start arguing about how the earth is actually flat. It's not round at all. I don't know if y'all are aware of that, but apparently it's becoming a thing again, that there are, you know what, let's not even go there. If you've ever looked at a large lake, you know that when you're just standing on the shore of that lake and you look out, you cannot see the rocks and the wharfs and the boats and the pylons and things on this other shore. That as far as you can see, all you can see is the surface of the water turning into the horizon. Well, that's because that lake has a radius of curvature, r. Now imagine that you put up a step stool or something here, and you stand on that step stool. And you do it without making fun of my drawing. And now you notice that you can just barely, now I'm missing the line here. You can just barely see a rock on the other shore of that lake. What have you got now? You know, this is R, and this, your eye has been raised up some height h above the surface. And you're now just able to see this, which means your line of sight is coming in tangentially to the curvature at that point, which makes this a right angle. Now you can estimate, and we're going to call it an estimation because we haven't done, this will be the most precise measurement that we make, will be the height h. But now we can talk about this length, r plus h squared, as being equal to what? This distance, d, and R. Now, if we square R plus H, then we end up with R squared plus 2RH plus H squared, and that is equal to R squared plus D squared. Now, I don't know about you, but when I see that, the first thing that I see is, quadratic equation. I don't remember the quadratic equation, and I don't want to. Okay, so, but if I have to, I know I can look up the quadratic equation. But look closely what we have here. Remember, the whole point of this exercise is to do rapid estimation. So we want to avoid the quadratic equation if we can. Well, the first thing I notice is, wait, I can eliminate R squared by subtracting it from both sides and end up with 2RH plus H squared is equal to D squared. Well, we are going to say that D was roughly measured as, what did they use in the book, 6.1 kilometers. Squared. And we will have measured height by measuring the height of the step ladder plus how far up from that we have to get to where our eyes, and we measure H as, what do they use in the book? 3 meters. So this is 3 squared, or 9 square meters, plus 2 times R times H. Point is, now the only unknown in that is the R, and we can algebraically solve for R. Do I need to go through and do the algebra to solve for R? Point is, it comes out to an estimation of approximately, and that's 6.2, 6,200 kilometers. Now, while we're here, I want to use this to segue right into the next and last bit that we're going to talk about for this chapter. That's dimensional analysis. Let's look at this equation right here and see, does it make sense? Okay, the fact is, in order to add two numbers together, they have to have the same units. If you're ever working on an equation and you notice that, wait, I'm adding square meters to Newton seconds, then you know you can't do that addition. You can't add different units together. Well, and you certainly can't set different units equal to some other units. Well, here we notice that we've got kilometers squared, which is actually meters squared. Okay, I mean, yes, we got it expressed as kilometers, but it's still square meters. Here we've got square meters. Here we have R times H. Well, what's R is expressed in meters. H is expressed in meters, so we have square meters. We have square meters, and if we factored out the 1,000 squared, we would have square meters. So, dimensional analysis shows us that this is correct, and that apparently at some point we took a square root and ended up with straight linear meters. This is the point of dimensional analysis. They do it rather formally in the book, where they don't worry about kilometers versus, meters, and they look at this is length, this is length, this is length. So they consider all of them as L in square brackets, telling us we have length, or in this case, that we have length squared. Length squared, length squared, length squared. If we were looking at doing something about velocity, then we would have length divided by time. Or we might have, if we were talking about acceleration, we would have length over time squared. If we were talking about forces, then we would expect mass times length over time squared. Kilogram meters per second squared. So, it's all fairly straightforward, but it's a very good thing to do anytime you're working on a problem. Be aware of your units. You can do a formal dimensional analysis if you want to, but even if you don't, always think about units. If you're adding two numbers together, now you can multiply different units together and come up with a derived set of units, or some derived unit. You can multiply mass times length and divide it by time, because multiplication and division are the same thing, just by a reciprocal. But in order to add numbers together, they must have the same units. And obviously, both sides of the equal sign have to be the same units. If they're not, something is wrong. Go back and figure out where you made a mistake. All right. That wraps up chapter 1. And Monday is going to be our exam on chapter 1. So Friday, we will, I expect by Friday, y'all will have some questions on some of the problems, some of the homework assignment. Come to class prepared to ask questions. I cannot stress this enough. I need feedback from you in order to know what I need to explain better and what you've already got. Otherwise, I don't know if I'm boring you explaining things that are like, duh, we've learned that 2 years ago. Or if I'm just zipping right past you, leaving you in the dirt thinking, wait, what? That doesn't make any sense. When's he going to explain what that means? I really do need the feedback from y'all. So show up Friday ready to ask questions. Let's get all of this, make sure you've got all of this sorted and straight in time for the exam on Monday. And of course, your homework will be due on Monday. So that's the other benefit of showing up Friday. You're going to get some free homework points by watching everybody work the problem together. And in case I haven't said this explicitly, I encourage you to get together and work the homework problems together. You'll be amazed at how much other people just brainstorming, working out an issue. You'll be amazed at how much difference it can make. And it's only cheating on the exams.